When we get together in class, I will share this toy with you. You may have already seen it um, in your life, but I call it a clicker. It's sometimes called a Newton's cradle, which is ironic because it is one of those unique problems that Newton never solved. It's not clear if he ever attempted it, but he was a member of the Royal Society in England at the time that this problem was proposed, and he did not come up with a solution. Instead, it was a man named Huygens that we're going to study who came up with the solution. But basically, you pull a ball out and you let it swing down here, and it hits, and all of these balls get knocked, but what happens is one ball leaves on the other side. Okay, kind of boring. But if you pull two balls back and let them go, so the two balls come down here and smack in, then what happens on the other side is exactly two balls swing out. And if you let three balls, you pull three back and let them go, wham! Then what comes off on the other side is exactly three balls swing out. And that's actually, it's magical to look at, and it's quite an interesting problem why it is that exactly the same number of balls leave as go in. And I will make it clear what a unique thing that is in just a minute, and maybe you will be able to supply the solution before I tell you. But before we do that, we need to look at collisions between objects. Here is object 1 with mass of 1, and initial velocity of object 1 is 1. And then here in this gray column, I have multiplied the mass times the velocity, which is a quantity that we're going to call the momentum of number 1. And we use the symbol P for momentum. That momentum is the product of mass and velocity. So here's object 2, its mass, its initial velocity, and this would be the initial momentum of object 2, the product of those two. And when I do it, I have a simulation. You may very well be doing a lab of your own, but let's look at that simulation. This is all set up with this one having a mass of, well, I'll show you. This one here has a mass of 1 and an initial velocity in the x direction of 1, and this one here has a mass of 2 and an initial velocity in the x direction of -1. So there were the initial conditions we were just describing, and if I run it, and this simulation does beautifully. They fall off the ends, and we could wait for this one. You could watch it. There we go. Not that much. Oh, it's beautiful, but that's too far. Let's run it again, and I'll stop it while it's still up here before it falls off the edge, and you can see that object 1 has a final velocity of -1.67 and an x velocity of 0.33. So that's what we have put in here, the -1.667 and the 0.333, and then you do multiply the mass times the velocity, you get the momentum after the collision, and multiply the mass and the velocity, you get the momentum, which really it would be better if this was 0.66666 and this was -1.66666, but we'll live with it. So the point is that you should look at what these initial momentums are and what these final momentums are and see some pattern emerging. We'll go ahead and do this next collision here, and for that one I want this one to have a mass of 1 but a velocity of 2. You're going to have to trust me that I'm changing the velocity to 2. And this one stays the same as it was, a mass of 2 and a velocity of -1. And if I run that one and stop them before they get off the shelf, you can see that this one has a final velocity of -2 and this one has a final velocity of +1. So, come on now. Oops, not you. Here you go. If I multiply the mass times the velocity for those two and do it here, this -2, I get a momentum of -2, and here I get a momentum of 2. Again, can you look at these two and see a pattern? Here is another. I won't bother to run the simulation for it. Momentum, initial momentums, final momentums. Can you see the pattern? Be proud if you can already see the pattern, and if not, here are some more results. Look at these two. Look at these two. What is a pattern? A pattern that is replicated in all 4 examples. Here we'll go ahead and do this one here. 2, 3, 2, -1. Okay, we'll run it. This one here has to have a mass of 2 and an initial velocity of 3. Oh, this will be exciting. Okay, run, stop. Oh, almost lost it. What suspense. And this one has a velocity of -1, and this one has a velocity of 3. Oops, yeah, there we go. So there you go, -1 and 3. So the product here and the product here, product, what's the pattern? Let's do this last one in the simulation. Yes, I'm going to reset this time. Okay, so this one has a mass of 1 and a velocity of 2. And this one here now, a little variation, has a mass of 2 but a velocity of 0. It's just sitting there waiting to be smacked. Okay, run, stop. And this was going at -667 and 1.33. Oops. -666 and +1.33. And you do the multiplication, and this is repeating 3's, and so I rounded that last 6 up to a 7. Okay, good. So, what is the pattern? Here are 2 more. These are collisions that we could do where instead of them bouncing apart, I make them stick together. They have elasticity of 0, and the result is that you get them approximately going at the same, here exactly the same speed afterwards, here approximately the same speed afterwards, that they're not bouncing apart, they're moving together after the collision. But again, the point is to look here and look here and look at these two and find the pattern. And I think the pattern's easiest to see in ones like this, where what is it about -1.67 and 0.67? And it is that they add up to -1, just as was the case with the 2 gray columns here. Let's take these two. They add up to +1, and if you add this quantity, -2.33 to 3.33, it adds up to positive 1. This one here, they add up to 2, and if you add those two together, it adds up to 2. Here they add up to 4, add those two together, they add up to 4. Here it adds up to 2, and if you add this quantity and that quantity, it adds up to 2. That this thing momentum is a quantity that is conserved. The total momentum before, that is the sum of the momentums initially, is the same as the sum of the momentums finally. If you want to play with that some more, you could go to this site, and I hope it's still working. It would give you a chance to put in whatever values you wanted and test this result. That there is this quantity called momentum, and you've already seen its definition. If you need to, go back to that slide. Its units, well, those would be the units of mass, which are kilograms, times the units of velocity, which are meters per second. So a kilogram meter per second is the unit of momentum, and that is what you're going to have to write. There is no simplification, no name like we did with the force, where we went from a kilogram meter per second squared and we renamed that a Newton. A kilogram meter per second just stays a kilogram meter per second. And this quantity, momentum, mass times velocity, is a quantity that is conserved. This is very important. In fact, a lot of the stuff we're doing does not work when you get into the realm of the relativistic, the very fast, or the quantum level, the very small. But momentum continues to be conserved in all of those realms. So momentum is a very powerful idea. It is only conserved, however, in a closed, isolated system. And it's very important that you remember those two. Closed meaning that no mass gets in or out, and isolated meaning that no force gets in or out. After all, what does force do? And the answer, I hope, that comes immediately to mind is that force causes acceleration. And what is acceleration but a rate of change in velocity? So if you had a force acting from outside, then you would get an acceleration, a change in velocity. Well, that's clearly going to cause a change in momentum. Similarly, if you change the mass, it's going to cause a change in momentum. So basically, what this profound statement is saying is that if you do not change the mass and you do not change the velocity, then the product of mass and velocity do not change. Which sounds vacuous, but in fact, that was poorly stated. Because it is okay for the mass to change. Look at this. The velocity to change, and it does change. It went from 1 to negative 1.67, and from negative 2 to 0.67. So it is okay for the velocity to change. It's just that the net velocity, that one of them increases, the other decreases, and the net velocity and the net mass stays the same, the momentum is conserved. So it really is a pretty powerful statement. But don't forget the fact that you need to have an isolated system. In fact, I think it would be a very good thing if you were doing a problem and you said, oh, well, the way to do this problem is to say that the momentum is conserved. And maybe you would write something like that. I would hope you would. Then off to the side, you ought to write this, that the net external force is equal to 0. No external forces, that is, no net external force. And if that condition is not met, then it is not valid for you to claim that momentum is conserved. Back to the clicker problem. And here you have a situation where I'm saying that each of these balls has a mass of 2, and one comes in and strikes with a velocity of 2, and suppose we just have 2 of them. So the other ball, also with a mass of 2, is sitting there waiting. Then the total momentum before that collision is 4 from this one and 0 from this one. The net momentum is 4. And after the collision, if the one ball that comes in stops, and the ball that was hit takes off with the same velocity, then you do have momentum conserved. But note, if you drop one ball in and then 2 balls go off together, each at half that initial velocity, that also conserves momentum. Or if the ball that you rolled in bounces backwards at the same velocity but in the opposite direction, and this one takes off at a velocity of 4, that would also conserve momentum. And there's where the problem comes. What we see is exactly the same mass, the same number of balls as you drop, is the number that goes out. But it can't be that that's because of momentum being conserved. We would expect momentum to be conserved here. But there must be something else to explain why exactly 1 and not 2, or 2 going off in opposite directions, or many, many other possibilities. And the person who figured this out was a Dutchman who was a contemporary of Newton's named Christian Huygens. And what he suggested was that in addition to momentum being conserved, this quantity, which you may or may not recognize as kinetic energy, needs to also be conserved in what is known as an elastic collision. If these balls are made of hardened steel, then you get a beautiful bouncy elastic collision. If the balls had been made of modeling clay, then they might have stuck together. And momentum would be conserved, but you would have 2 balls going out instead of 1. In the condition where it is an elastic collision, you have 1 ball going out. And you can see that the kinetic energy after the collision in this case is again 4. But in this case, if you take 1/2 this mass times that velocity squared plus 1/2 this mass times that velocity squared, you get a 2. In that collision of inelastic objects, a tremendous amount of kinetic energy disappears, half of it, and becomes internal energy, heat of these 2 objects. It's actually going to be much more than well, we'll let it alone. In the case where they bounced apart like this, you have much more kinetic energy after the collision than initially. If you have exactly as much kinetic energy after the collision as before, then that uniquely forces exactly the same number of balls going at exactly the same velocity to come off the other side as went in. All right, so problems with collisions. Very important that you notice that they say that they stick together, and they drew a picture of them sticking together, but they won't always draw the picture. That in this case, kinetic energy would not be conserved, but momentum would, because it's only one ball pushing on the other ball and the other ball pushing back. Those are internal forces between the 2, not an external force. So momentum will be conserved. Here, I need to establish good habits. We ought to write out here. Yes, I've checked it out. And the sum of the external forces is 0. You write that. Whenever you want to say this, you assert that, yeah, I checked it out and it's good. Momentum should be conserved. And then under this initial momentum, I wrote the momentum of 1 and the momentum of 2 initially. And here I wrote the momentum of 1 and the momentum of 2 finally. But these two will be moving together if they stick together. So V1 and V2 final are going to be the same. And so I can rewrite this expression like this. Now, if you will put in the mass of 1 and the mass of 2 and the velocity of 1 and the velocity of 2, and again the mass of 1 and the mass of 2, then the only unknown will be V, and you can solve it. And I would expect you to do that and get your answer on the worksheet. Now we have it without the formula written out for you and without pictures. So stick together. You need to realize what that means. You need to do this problem, and in this case it is multiple choice, but I would like you to show your work, including writing P equals P and sigma F external equals 0. Now a more interesting problem, we have this T-bone crash, and in this case we have a sporty red sports car coming up and this other car coming in from the side. And in this case it is actually the fault of this car that there is this collision between the two. This guy crashes into the side of that car, and the two of them then go off at this angle. And by looking at the angle they went off of relative to the initial, it is possible to know what the initial velocities of these two cars are and to know who was speeding in that collision. For example, instead of cars I have balls, but here you have this 6 kilogram ball going in the x direction at 2 and this 2 kilogram ball going in the negative y direction at 2, and they collide, and this time they do not stick together, but they bounce apart, and after the collision the 2 kilogram, here's the word after, the 2 kilogram ball is going in the positive y direction at 1, and the 6 kilogram ball is going at what direction? And you were to figure that out. And in this collision that takes place in 2 dimensions, I would strongly suggest that your approach be to look at the fact that the momentum is conserved in the x direction and that the momentum is also conserved in the y direction. I say that momentum is conserved component-wise. And so you set up these equations. Notice the y's and the x's. And then you carefully substitute the values. And you could stop the show. And you could finish this problem. Or you could be lazy because I'm about to drag some numbers on. Assuming you have not stopped the show or that you're starting it again, it should have looked like this, substituting for mass and velocity of the objects. Notice that the x velocity of this one, of number 2, after the collision is 0. It's got velocity, but no x velocity. And then you put in the y, and notice this one has no y velocity before. This one does have y velocity. And that this one, I don't know its y velocity, but this one has a y velocity of positive 1. Well, if you solve these, then you can get that the x velocity of number 1 is 2, and the y velocity of number 1 is negative 1. That is the only way to conserve the x momentum and the y momentum in this collision, which means that this object here is going in the x direction at 2 and in the y direction as 1. You need to add those graphically, not graphically, but paying attention to them being vectors to get the magnitude of the velocity and this direction that it is going. That would be south of east. And again, you could stop the show and you could do that. Here is the answer. That this should add up to 2.2 meters per second, and this angle here should be 27 degrees south of east. Thank you. That concludes our experience today.